So we're just gonna start with the basics for a couple of days and then we'll move into the things that are get a little bit harder. Remember, a chemical equation represents a chemical change, not a physical change. So if a chemical equation is written properly, then it's going to represent a chemical change. And if it is balanced, then it upholds a couple of different laws that you need to. So the things that are required are the equation itself. Remember, you start with the reactants, so they are on the left. Head of the arrow. And then my products are going to be on the right side of the arrow. And yield. The law of conservation of mass and energy, those laws are what govern writing a chemical equation, more so with us, just the one that's the law of conservation of mass. And those say that atoms and energy are neither created or destroyed during a chemical reaction. So that means that they have to be equal on my reactant side and equal on my product side. So we have to have the same number of atoms on each side. And that kind of what should have been something about that should have been your answer to the journal. The states of matter should be indicated with each product and reactant. We'll do that some, but you don't have to do that on every equation, and we'll talk about that more. Remember that you have to memorize your diatomics. And when they are alone, they need to be two atoms together. So in other words, if I have nitrogen plus oxygen as reactants, they're by themselves, so they exist as diatomics. But when they come together, and a part of a compound, now you don't have to necessarily worry about them being diatomics or having a subscript of 2. Now they're both stable because they're bound with another atom of a different element. There's also that are called some that are polyatomics. So if we have sulfur and it's all by itself, it exists as 8 atoms together. And then phosphorus, all by itself, it exists as 4 atoms together. And once again, that's just when they're by themselves, not part of a compound. Remember, in chemical reactions, whatever the subscripts are on the reactant side are not necessarily going to be the subscripts on the product side. So you don't carry those over. Sometimes they may be, but sometimes they may not be, depending on what they combine with. All chemical changes are accompanied by some change in energy. That's called thermochemical reactions, which we cover more in another unit. So a reaction that releases energy would be exothermic. And then a reaction that absorbs or needs energy on the reactant side would be considered endothermic. So whenever a bond is broken, energy is released. That's not what I meant to put. Let's put energy is absorbed, sorry. So that bond breaking is usually happening on the reactant side. And then whenever a bond is formed, and that one is going to be the one that you have energy released. So an exothermic reaction is usually going to be more spontaneous, happens more quickly because it's moving toward a lower energy level. All right, let's look at some of the things that we will see. So plus sign is just going to separate your two reactants or your two or more products. Arrow means yield. It doesn't mean equal to. If you have an equation that is reversible, then you're going to have a double-headed arrow. If you have S in parentheses and it's a small s, so like let's say we produce sodium chloride, it would have parentheses with a small s behind it. That means that that compound, that element is in the solid state. You can also have an arrow going down, which represents a solid, but only if it's on the product side. That means that you would have had a precipitant. Oil means it's a liquid, and that's not the same thing as something being dissolved in water. That would be considered aqueous or AQ. So bromine, for example, it's blue on our periodic table. It would be an example of a liquid. But if I had sodium chloride dissolved in water, that would be an example of an aqueous solution. G, gas. And same thing, if I have an arrow going up, then that means there is a gaseous product. If I have my yield arrow with a triangle above it, that means heat had to be supplied for that reaction to occur. Then the last one, if I have an arrow with some kind of compound, I'm just going to put MnO2 as an example. Over the top of it, that means that that compound over the arrow is a catalyst. And if you remember from biology, catalysts are not used up. So that's why it's written over the arrow, because it will not undergo a chemical change. It'll just speed up the reaction and still be left over. Balancing. So the first thing you have to start off with when you're balancing his equation is you need to do an atom inventory. How many atoms you have of each thing? Those are already equal on both sides. You don't have to worry about balancing it. So you want to count the atoms on each side of the equation. We need those to be the same for us to have it balanced. We practiced counting atoms whenever we did molar mass. Remember, the subscripts are the small numbers within a formula, and that tells you the number of atoms that are in that compound. If there's not a subscript, then it's an assumed one. So here, MgCl2, that means I have just one atom of magnesium. And since the Cl has a 2, that means I have 2 atoms of chlorine. Same thing here, tin nitride. They both have subscripts, so that tells me I have 3 atoms of the tin and 2 atoms of the nitrogen. The coefficient is what we use to balance an equation. And that's the large number in front of the formula of a compound. It tells you how many molecules, formula units, elements, or moles you have of whatever compound you're looking at. And you, just like with the subscripts, you will never use a 1. If it doesn't need a subscript, you just leave it blank. So with a coefficient, to get your atom count, you're going to, first of all, find your atoms in the compound and then multiply that by your coefficient. So in other words, we said a subscript only affects only the atom that it's behind, but a coefficient is going to affect everything that follows it. And that's also why it makes some balancing of some equations a little bit harder. So if I look at this one, sodium sulfate, to start off with, sodium has 2 atoms. I have my coefficient of 3, so 2 times 3 would give me a total of 6. Sulfur, I have a assumed 1. 1 times 3 would give me 3 atoms. And then my oxygen, subscript of 4. 4 times 3 would give me 12. Don't y'all try that next one, and instead of atoms of sodium, it should be saying atoms of calcium. So find out how many atoms you have within the compound and then multiply that by 4. All right, so how many atoms of calcium did we get? 4 times, is that a 3? I can't read. Is that a 3? Yeah. So 3 times 4 would give me a total of 12. Phosphorus, how many would I have? 8. Is because this 2 is behind the parentheses, that means I have 2 phosphorus. And 2 times 4 is 8. And finally, my last one, my oxygen, 32, right? 4 times 2 is 8. 8 times 4 is 32. All right. So whenever you're balancing equation, you need to do your atom inventory. You need to have the correct formula. We're going to start off and you're going to have the formulas, but starting next week, you'll have to write the formulas. That's why we did the little nomenclature review. Once the formulas are written correctly, do not change them again. What that is saying, you can't change, excuse me, subscripts to balance. That would be a nice, easy way. Can't do that. We're going to have to work around the subscripts by using our coefficients. Atom inventory for both sides of the equation, and then you use coefficients to get it balanced. So I'm going to show a process that's you kind of make a table of this. You don't have to do it. Some people will be able to do it without the table. Some people probably can do the simple ones without the table, and then they may need the harder ones sometimes. But I'm going to show it the longer way, and then you can adjust to what you need. We're just going to do a couple here, but most of our practice we're going to do on the practice that's in your notes. All right, so first thing I'm going to do, I'm going to take an atom inventory. So if I look at my reactant side, I have hydrogen and I have oxygen. That on my reactant side, I have to have those same things on my product side. I like to try to keep them in the same order so I don't get myself confused. So first thing, we're going to see what we have to start off with. So I have 2 hydrogen because of that subscript of 2 and 1 oxygen. Go to my product side, I have the 2 diatomic, so that means I have 2 of each. So that is not balanced. If that was balanced, they would be the same on both sides. Hydrogen looks good, but my oxygen, I have 2 here, only 1 here. So that means what do I need to come and put in front of the water? So I will end up having 2 oxygens. I need 2, I have 1. What times 1 equals 2? 2. So I put my 2 here, which is going to change my oxygen. 2 times 2, it also changed my hydrogen. So that means I have to work back now. I have 2 hydrogen. I need 4. So what do I need to put in front of that diatomic to end up with 4 hydrogen? 2. Do that, then I would have a balanced equation. And that's usually how they work. Usually you fix one thing and it messes up something else. So you kind of have to go back and forth. Remember, this 2 affects everything behind it. So even though I only want it to change the oxygen, really, it's also going to change the hydrogen. I have people who like to do this. They say, okay, I need 2 oxygen. So they like to come and try to put that coefficient in the middle of the formula. You cannot do that. Coefficient has to go at the front. All right, any other questions on that one? And then we were to skip to where we have a little bit more room. If you have a polyatomic ion, so like here we have nitrate, it is usually easier to keep those together as one thing or one entity as if possible. So in other words, when I look at this, I'm going to have lead, I'm going to have nitrate, and then I'm going to have sodium. Like I said, we're going to skip that next one. So if you need to write down, you're not going to have anything else to write. Those are my 3 things I'm going to count. So I need them on my reactant side and I need them on my product side. All right, so let's start on my reactant side. Lead, no subscript, so I just have 1. If I look at my nitrate and I'm keeping it all together, since there's a tube on the outside, I have 2 nitrate groups or 2 nitrate polyatomics. And then I'm going to go to my other side and, oh no, it's almost sodium. 1 sodium. Now let me go to my other side. Lead all by itself, so just 1. Nitrate, not in parentheses, so that means I just have 1, and sodium, I just have 1. That's what we have to begin with. Same thing, if they were all equal, then we would be through. But in this case, the nitrate, there's 2 on the product side and only 1 here. So I have to go to the compound that contains nitrate. I'm on the wrong side. Compound that contains nitrate and put a 2 in front of it. So by doing that, that changed my sodium to 2 and my nitrate to 2. So sodium we really didn't want change, but at least it will be an easy fix. I have 2 on my product side, only 1 on my reactant side. So what I need to put in front of my sodium, what coefficient? A 2. And it's nice because it's an element all by itself, so it doesn't mess anything else up. All right, any questions on that so far? Have y'all done this before in middle school? Page where there's actually more room to work. And let's just do some different types of examples here. So usually you're going to see your equation written like this. You're going to have more room. So I like to draw my line down the middle where the arrow is. Once again, you don't have to do this. Some of y'all will be able to balance without doing this. So it's not required. So I only have 2 elements, iron and oxygen. All right. So on my reactant side, I have 1 iron atom, and then because of my subscript, I have 2 oxygen. On my product side, I have a couple of subscripts. So 3 affects my iron and 4 affects my oxygen. So that's what I'm starting with. Not all equal. That would be nice if they were. So if I start with my iron, I have 3 on one side and only 1. So I'm going to go to my smaller size. side, I'm sorry, that's the one that needs to increase. So what do I need to put in front of my iron? 3. Once again, it's all by itself, which makes it nice because it doesn't mess up anything else. And same thing with my oxygen. I need 4, I only have 2, so I need to put a 2 in front of my oxygen. And then that should get me balanced. So that's what I mean. It's nice when they're all by themselves, not part of a compound, because it makes it a little bit easier. All right, why don't y'all try 2 and 3? For number 2, did we need a coefficient for the SR for the strontium? What do we need? But we needed a 2. And diatomic oxygen, are we going to need a coefficient for it? 2. And then my compound, strontium oxide, does it need a coefficient?
Yes.
So probably the way you address this is you notice the oxygen and then that changed your strontium. Sometimes you may, I don't think I've come across any examples on the ones I've done. Sometimes you may put a coefficient in one place and find out you need to come back and change it, which that's fine also. I'm going to write something. Do not write this because it's not correct. So let's say that you went to balancing things, or you can write it if you want to and just say not correct. So let's say somewhere that you went to balancing, and then somewhere you got a little bit lost and you ended up with these coefficients. That would be incorrect because you need to have your coefficients be as reduced as possible. So in other words, all of those can be divided by 2. So that's what would make those other numbers incorrect. You have to have them reduced as far as possible. Sometimes on the harder ones, at least for me, if I get lost in it and I can't get it balanced, sometimes it's easier to start all over. All right, number 3, potassium K. Do we need anything?
Yeah.
What do we need? 2, bromine liquid. Oh, potassium bromide. 2. So it was pretty much just like number 3. All right, I'm going to skip down and we are going to come back and do number 4, but it's harder. So we'll okay. This one, number 9. I'm trying to show you examples of some of the things you might come across. So I think that's a good one. All right. This one I'm using it as an example to show you a polyatomic. So iodate, that's one of our polyatomics. So I'm going to keep it together. It's on the reactant side. It's also on the product side. You can separate them out if that's something you decide you're more comfortable with, but usually it can, that sometimes will make it a little bit more difficult and a little bit harder to balance and longer. So I'm going to work it this way. Barium, chlorine, potassium, and iodate. All right, so first of all, just gonna do my inventory. Ba, barium, only 1. Chlorine, 2. Potassium doesn't have a subscript, so just 1. And once again, if I think of that as one thing, there's only 1 of those. Then I'm gonna come to my product side. Barium, still just 1. Chlorine, 1. Potassium, 1. But now, because this iodate has that 2, I'm gonna have 2 of the iodate groups. See where we're at. So barium looks good, but my chlorine is off. I have 2 on my reactant side, only 1 here. So I need to put a what in front of my potassium chloride? A 2. So that changed my chlorine, which I wanted. And it also changed my potassium. So that means I'm gonna come back to this side, do the same thing. I only have 1, I need 2. So I need to put a what in front of the compound that has potassium? 2. So that changed my potassium to 2. And it also changed my iodate to 2, which is what I needed. So that is balanced. Sometimes, like on these, if this makes it a little harder, I'm going to leave the polyatomic to the end to hope it works out. But that's when you're balancing, a lot of times you're kind of be going back and forth, and then one thing will kind of get the rest of it balanced for you. All right, let's flip back to that other one. It's really making me use my medical skills. All right. This type of reaction is called a combustion reaction. 5 different types, we will separate them all out. This particular type is called a combustion reaction. It's with a hydrocarbon or carbon that contains hydrogen and oxygen is combusted or burned in front of oxygen, and you always get these 2 products. So these will be real easy to write. At this point, we will have been using our ion sheet for days on end. So this is nice when we get to that. But sometimes they're the harder ones to balance. All right, so I only have 3 elements. So to start off with, my carbon 8, my hydrogen 18, my oxygen 2. Right, same thing on my product side. My carbon, no subscript, so just 1. My hydrogen 2. What makes these a little bit difficult is the oxygen. Oxygen we have right now. 3. Or anytime you have an element that's in a couple of different places, I would save that to the last. So I'm gonna start with my carbon. I have 8. Over here, I only have 1, so I need to put what coefficient in front of CO2? 8. So. All right, so that changed my carbon to 8. But it also changed my oxygen 17. Another thing that's going to make it difficult is you're going to have oxygen as an odd number. And no matter what I put in front of this diatomic, it's going to have to be an even number. So that's another thing that's going to make this a little bit harder. All right, 18 hydrogen, only 2 here. So I'm going to put a 9 in front of here. 9 times 2 is going to give me 18. All right, let's see how many oxygen we have now. From here, 8 times 2 is equal to 16, plus another 9. I'll fill this out too. Is 25. Am I right on my math? All right, so when you get to this point and you have an odd number, then you're going to have to do a little trick. And the little trick is that you are going to multiply all of your coefficients by 2. So 1 times 2 is 2. 1 times 2 is 2. 8 times 2 is 16. 9 times 2 is 18. Right, everybody. So now let's see what we got. We got 2. 18 times 2 is going to give me, for my hydrogen, 36. 2 times 2, 4 oxygen. We really have to worry about carbon. This isn't right. This should have not been 2. This should have been what, y'all? Now I'm gonna go this side. 16 carbon, because that's all I have. 18 times 2 would be 36 hydrogen. And then my oxygen, I'm going to have 16 times 2, which is going to be 32, plus my other 18, which is going to give me 50. So I need 50 oxygen. So that means I need to go back and put what in front of my diatomic oxygen? 25. Some of them are even longer than that. So we will do just this section time later on in the week. But if you come across one of these, sometimes they're just harder to balance. But that's a little trick that you can do. All right, why don't y'all take a few minutes and try some of your other practice ones? Should have time to do a couple. I'll see if anybody needs help.